Respect. All right. Okay, are you guys ready to climb all the way summit of this big mountain? And we're speaking about the big mountain, much bigger than Mount Everest, way much bigger than that. So today we're gonna continue to discuss about how is that we can express forces in terms of generalized coordinates. Remember, the story is such that now we're in a dynamics, and dynamics is all about force equilibrium. How is that the forces, which are, we have two different kind of forces, inertial forces and external applied forces. How we can set those two set of forces to be equilibrium, making them to be equal, and express all that using generalized coordinates. That's what we need to do today. And once we know these forces in terms of generalized coordinates, then we are ready to start solving our unknowns. Our unknowns are generalized coordinates. That's what they are. Okay, so generalized inertia forces, but prior to that, there's quite a bit we need to discuss about generalized externally applied forces. And let me just make this clear to you. It's all about this. F equal than mass multiplied by acceleration. This one here is external applied force, meaning that if you have a box like this, sliding in the surface, it's a force that is making this box to move right, left and right. So we can put the force like this. And how much is moving? That is expressed by inertia forces. Inertia forces is a mass multiplied by acceleration. And what we do here is that we will solve this guy from this equation of motion. And it's going to be simple like this. So it's going to be r dot dot equal the F divided by mass. And then we're going to integrate velocity out of the acceleration. And then position out of the velocities. That's how it goes. That's how we're going to solve the equation of motion. Makes sense? But prior to that, so there's something we need to do. Something we need to do is that we have to convert this force to be expressed by using generalized coordinates. That's a challenge. And we can make it happen using this concept called virtual work, virtual displacement. Virtual displacement is actually the one that creates this mapping between two different coordinate systems for us. Okay, so now this is a news flash. So in 3 weeks, there is going to be MEVEA, 9th annual MEVEA online seminar. And this used to be a lot of fun. Usually it's a lot of fun. A lot of good presentations about different subject matters of simulation, real-time simulation in particular. And I recommend you to consider to participate. And it's free of charge, of course. And usually the presentations are coming from different companies worldwide. And they're telling how is it they're using real-time simulation and advanced simulation tools in their product processes. So that's going to be October 19th. And the details you can find by logging into MEVEA website. Now, what is it we discussed a week ago? So a week ago, we were able to close the kinematic analysis. And now, please understand this. Kinematic analysis is not about forces. There's nothing whatsoever about the forces. It's everything needed to carry out the kinematic analysis is a constraint equations, nothing else. How much we need constraint equations? As many as unknowns. What are the unknowns? Generalized coordinates. So we have to have equal number of constraint equations and generalized coordinates. Then we can solve it. And we're solving this problem by using 3 different steps. First step is it is a position level solution. It is an iterative process. So it's not the solution we can get automatically. or easily, but instead we need to repeat this iterative solution certain number of times. How many times? Well, that depends on the accuracy you are after. So if you really want to get accurate results, you need to make sure that this Newton's difference that it is telling how to update the coordinates is becoming very small in length. So that's the way to minimize the error related to iterative process. Now, once you're done with your positional level analysis, then you can move on to next level, which is acceleration, velocity. And the velocity you can get by differentiating this equation once with respect to time. And you will get this one. Now, you set this equation to be equal to 0, and you can solve this one, velocity. And then you differentiate the same equation one more time with respect to time, and you solve this guy, acceleration. And that's how it goes. So velocity is a matter of substitution. Acceleration is a matter of complicated substitution, nothing else. Okay. All right. So just taking what are the comments from the online participants. And this is this positional level iterative process. So it goes, that's the way that we first create the constraint equation, and we compute the Newton difference. And we compute the Jacobian matrix, then we compute the Newton difference. And then we're ready to update our coordinates. We update the Jacobian matrix and constraints. We check how good is the solution. And if it's not good, we repeat it. And that's how it goes. That's a positional level analysis. And one thing that is needed here is this Jacobian matrix. Now, I'm going to ask very soon in my first in-class quiz what this partial operation stands for. What is a physical interpretation of this partial operation? There are mappings from one coordinate system to another coordinate system. In Jacobian matrix, it is constraint equations to generalized coordinates. That's what it is. What we're going to do in case of forces is that we will introduce the mapping between the global coordinates and generalized coordinates. So it's all the time mapping from one coordinate system to another. Okay? Or maybe it would be more correct to say that one set of variables to another set of variables. That's what it is. Okay, Jacobian matrix tells you the dimension of your problem. And in the kinematic analysis, Jacobian matrix must be skew. You must have equal number of constraint equations and generalized coordinates. Otherwise, you are not able to invert this matrix. There may be the cases that you're still unable to invert it, but let's just say that those are special cases which we are not going to discuss in this course. Okay, and here comes this grand challenge. The grand challenge is this, that we have force vector that is expressed using global coordinates. Force vector, which is F here, having the projections in global X and global Y axis direction. Now, what we wanted to do here is that we wanted to convert this force to be expressed by using generalized coordinates. Okay, so it's a one body we are looking here. So how many generalized coordinates is in a one body? Everybody needs 3 generalized coordinates. So you see already here that this is not useful as it is for us. Why? Because numbers are not matching. There's 2 components, and I'm looking for 3 components. So how can I get this mapping? Remember, the mapping will come from the concept of virtual work, and more specifically, concept of virtual displacement. And that gives you this relation where I'm saying delta R is equal than partial R partial Q. This is partial. multiplied by delta Q. Okay, so this is pretty much as complex it can get. But what is that we have here? So we have here vector r, which is expressed using global coordinates. This here consists of two components, which are projections along x and y axis. What is this one here? This one here is vector of generalized coordinates. How many components? 3. And what is here? This one here is this magic mapping from one coordinate system to another. We're using this magic mapping to convert this force to be expressed using generalized coordinates. That's it. And then we will do the same for inertial forces. And then we're done. Then we're ready. Then we're ready to express equations of motion. And that we still need to get constraints into account, but it's not going to be too complicated at all. So it's going to be pleasant. All right, so that's where we are at. You're still with me? Okay, so it's like, well, it's more like this, right? Okay, good. Okay, work is the concept that gives us this mapping, this magic mapping for us. Okay, I promised a week ago that we can compare the work, real work, and virtual work to see what is the difference. Okay, so by the definition, work is displacement in the direction of force multiplied by force. So in multi-body terms, how is that I can express displacement in the direction of force? Okay, in the direction of force is going to be difficult, but let me just say in general way that I have here point O in a certain time and the same point O after a little while. So that's a displacement. So it could be like, let me try to make it here, potato. So this is a global coordinate system. This is my O, and I'm expressing O using this only kinematics that I know. When it moves here, this is this component here. When it moves here, the same point will be expressed like this. So the difference is a displacement. So this displacement is when I subtract these two vectors from each other. Okay, that's displacement in the direction of force. Let's say that the force is applying in that direction, roughly like this. Okay, now I can call this as a delta R, which is my displacement caused by this force vector. Now, in real life, when I look mathematically, what is this delta R? It's not possible that delta R will take a place or will happen when the time is not running, because we don't have a time machine. So we have to consider time. When you consider this delta R, you have to express it in a way that is a partial R, partial T multiplied by delta T, meaning the time that it takes to do this displacement. All right? And then plus partial R, partial Q multiplied by delta Q. Remember what I said a week ago. I said that virtual displacement and virtual work is like real work, with the difference that we are assuming that the time is not running during the displacement. What the heck that means? Like how you can make displacement like that in the real life? Well, you cannot. I mean that you need to create this time machine and all that, so it becomes to be cumbersome. Not easy, but it's a mathematical concept to introduce this mapping for us. So it's a concept. It's a tool set. Don't think about it like, okay, what's the color of virtual displacement? Nothing concrete like that, because you get very confused as soon as you started to think about it like that. So that's not the way to go. Okay, but it's a tool for mapping. That's what it is. Okay, so in virtual work is all the time like this, except this component will disappear. And also another thing is that I'm calling this displacement to be very small, virtual, very small displacement. So instead of using delta, I'm using delta, but small delta, because it's such a tiny small displacement. Okay, now, really the magic that I'm after is this one. What I just wrote it in my previous slide. Delta R is equal to partial R partial Q divided by delta Q. And next give me partial R partial Q multiplied by delta Q. That's what it is. Now, what is this mapping? What are the components this matrix is mapping together? Well, one component is global coordinates, right? What is another component? Generalized coordinates. Because this one here, global, this one here, generalized. That's what it's doing for you. Okay, so you're with me. Very good. Just checking. Just checking. One day I will make experiments like how long it takes that I'm quiet before you say anything at all. All right, it's not going to be today. Okay, here's the full cycle. So virtual work is a force multiplied by virtual displacement. Why? Because it allows us to express this force in terms of generalized coordinates. Okay, so I'm using this magic mapping, and this magic mapping can be expressed in details as it is shown here. So as a result, I will get the vector of three components. There is this vector force Fi, which is force is in global x and y direction, and the third component, which is how much moment is imposed to generalized coordinates theta. That depends how far you are from the body coordinate system. So it's basically, if this is my body, this is my body reference coordinate system, the force is applying here. So it's this level arm, this direction, x multiplied by force, because that's the one that makes the system to rotate with respect to coordinate theta. Right, so it all makes sense. Is it so? This all makes an awful lot of sense. No comments. You want to keep it as your private information. Okay. All right. So that's what it is. So this is this third component is a moment due to the level R. How much is a moment? This third component, if I have here potato-shaped body reference coordinate system is located in the center of the mass. Gravity is applying in the center of the mass here. How much is this third component? How much is introducing? How much is how big is a level arm? 0. So this one here is 0. So if this is 0, how much is the entire equation? 10 or 0? 0. Because it's all the time multiplication, so it's 0. So meaning that the third component is 0. Because it's applying in the center of the body reference coordinate system. That's what it is. Okay. Physical interpretation of matrix, partial R, partial Q, and the game is on. Success rate. And the options, let me read the options first. Define relationship between the global coordinates and constraints. Constraints. Define relationship between the constraints and generalized coordinates. Defines relationship between the global and generalized coordinates. Defines relationship between external applied forces and constraints. One only is correct. And Socrates is on. Okay, and the success rate cases are 0. No, that's not even possible statistically, so it needs to be higher than that. But how much higher? 100%? 19, 90, 90. It could be that high, 90. Oh, they complain that there is a difference, the quiz is not matching. Is that correct? So how is it not matching? So what are the options you see in a in-class quiz? So what they say? So options are different. Okay, let me go and take a look. Okay, sorry about this. Now you're gonna lose my. Mm, okay, so okay. So here, this is better. Interpretation of matrix. In the case of virtual world, defines a rotational particle. Here it comes again. Rotational particle. It always comes. Defines a body dimensions. Defines relationship between the global and generalized coordinates. Defines relationship between external applied forces and constraints. Oh, this is much better than it is in my slide. But you don't see it now at the moment. So just a second. Okay, you see, not yet, but it will be there momentarily. Yep, here it is. Here it is. So you see that all the options are. Am I blocking the view? Not much. So this one is easy. Would you like to change your answer regarding the success rate? I figured it would make sense to increase the number a bit. But how much? I don't know. How much? 95. Okay, would you like to learn what is my guess? 110. No, 100. 100%, because this is, okay, this is easy. This is easy. Just focus. Don't get, your fellow students to get you confused, because you know the answer. You know the answer. And the one way to find the answer is eliminate the ones that are not making any sense. Okay? Okay, now the cases are 99%. That would be outstanding. I'm not going to dance today because I feel tired today. Maybe you recognize that already my voice. But I'm not in a, it's not common that I don't feel extremely strong. I feel only strong today. So, what a disappointment. Okay. Okay, there is somebody is saying that for sure it's our favorite option will be watered at least once. What is his favorite option? You only know that. Okay, by the way, one thing that I don't know if you look at these recordings after lecture, but if you do so, I recommend you to use a closed capturing. It helps quite a bit. It helps a lot because some of the things that I'm pronouncing are coming with an accent because I do have an accent. But YouTube is clever enough that it can recognize my talk. It can make me clear. What do you think about that? That needs an awful lot of CPU power. Okay. All right, so let me see how many cases we have. 82 votes. That's roughly the amount of votes we get usually, is it? Always. Okay, so we'll close it in 5, 4, 3, 2, and 1. Okay, all right, so let me get started from the good news. Defines the body dimensions, 0%. That's a good news. But then rotational particle, I think that I need to just take that off from the options because there's always somebody playing safe, avoiding that. And that's 2%, and defines the relationship between externally applied forces and constraints. No, that's not the case. That is not the case. It is relationship between the global and generalized coordinates. And now, excuse me, I need to take this back to the PowerPoint presentation. This one here, and how it went. First, this. Oh, you see it already. But I think this is now in a presentation mode that I can't make any drawings. Okay, here comes pretty much the example that I've explained to you already. So I have here a beam-like body, and in the center of the mass, there is a gravity force applying in a minus global y direction in this system, and I'm asking you to create the vector of generalized forces, generalized external applied forces, using the information you just learned. So it's all about this force, by the way. Please understand that it's always pointing downwards. Yeah, I know what's the problem is. I need to change these settings a little bit. Okay, and this back. You see nothing yet. Okay, here it goes. All right, so force is applying in the center of the mass, but body reference coordinate system is not located in the center of the mass, but instead it is at one end of the beam-like body, this end. And the force vector is this. So its x component is 0 because the gravity is pointing downwards. Y component is a minus mass multiplied by gravity constant. Okay, how many components I will get when I express this by using generalized external applied forces? 3, because everybody needs 3 generalized coordinates, meaning that this force expression must have 3 components. Some of them may be 0. Like this one here, I don't see any way that this will be other than a non-zero, but 3 components is the one that we're looking here. How can I do it? Very mechanically. So I will take my partial operation where the force is applying here, and I'm using my kinematic expression to do it, and that is then multiplied by the force itself. And I made a little bit of shortcutting here because this was offered a week ago, this mapping matrix. So there is a submatrix which is 2 by 2 identity matrix, and then this component where I have my rotation matrix differentiated with respect to angle theta multiplied by vector u bar, telling where exactly the force is applying. Okay, so only thing that I need to do is that I need to substitute the right kind of the things to this matrix. The vector u bar is going to be L divided by 2, 0. Because we are located here, free end of the beam-like body, and the x-axis is pointing upwards. And that's how can I tell? That's how I can know that the distance that I need to travel along the x direction is L divided by 2, positive direction. All right. Then the rest is just a substitution, and this is my force vector. This is what I'm gonna get as a result. Always, if there's a one body, that must have 3 components on its generalized forces. Always 3 components. Okay, so that's what it is. Let me ask you this. Now the same setup with the difference that now the body reference coordinate system is located in the center of the mass. Exactly like we discussed a little while ago. First thing I'm expecting you to do is that think about how many components are needed. All right? And then the last reasoning you need to do is related to how much moment arm is introduced in this particular case. All right? So then let me just put the Socrative on, then you're good to go. Okay, so it's all about, take a look at the slides. Uh, Sorry. Okay, so would you like to get some more time to answer this, or is it all clear? Pretty clear. Mo- Oh, I'm sorry. Okay, let me. No, I'm sorry, I made a mistake. So it's a wrong order, so it needs to be this way. Ah, okay, so these are the options. Oh yeah, I'm sorry. I'm sorry. Duplicate. Okay, here it goes. All right, get started by counting the number of components. And think about how many generalized coordinates is needed per body. Everybody needs no law. Okay, I'm not going to tell anything else because, the risk that I need to do something stupid is increasing quite significantly. So I need to go easy here, not providing you any more instructions or tips. Okay. So can you guys make me a big surprise? I score 100%. And the game is on. Okay. So YouTube algorithm is suffering because of me. So I got that message from the chat. Yeah, particle option is missing this time. So here comes the good news. So no one can vote rotation of particle this time. So we have some good news. So don't put, something else. Rotation of particle. Not mentioned in these options. Okay, I don't see the in-class quiz in Socrative, but I think that I will go. I have one more example here. So this is classical way to express the generalized external applied forces. A little bit of weird too because I have here a triangular shaped body, and in the two corners of triangular shaped body I have force, which is expressed by using global coordinates. It's always pointing this direction, meaning that even when the triangular shaped body is having this configuration, the forces are still pointing this direction because they are expressed, the forces are expressed using global coordinates. All right, so what I need to do is that I need to express these two locations, A and B, using the only equation that I know, which is this one here. And then I differentiate that equation with respect to my generalized coordinates. And that's it. I will get the two different kind of mappings, one for point P, another one for point A. And then I'm done. It goes like this. A point, the one that is located in the lower corner of the triangular shaped body. So I'm expressing that location using this equation that I just explained to you. I'm going to substitute the information regarding the vector u bar to my equation. The vector u bar is mentioned in this example. And then I'm differentiating, first of all, I will get the vector of two components because this is in global coordinates. I will differentiate this with respect to my unknowns, which are my Rx, Ry, and angle theta. And I will get this mapping. This mapping matrix, the only thing left here is multiply forces with the mapping. And I will get the three components. And the three components are the ones that are shown here. Okay? And I redo it, but this time for point B. Point that is located here. So the only difference really is vector u bar, nothing else. So here's a vector u bar. Here's my vector, which shows point P with respect to global coordinate system. I differentiate that with my variables. I get this mapping matrix, and here's my final solution. Now I just need to add these forces together because they are applying in the same body. I'm summarizing force 1 to 2, and that's what it's going to look like. Very mechanical. No thinking whatsoever. Mechanical doing. Mechanical do it over and over and over again. No shortcuts, no clever ideas, because as soon as you do that, you go south. Okay. All right. So the moment. Well, moment is very simple because it's applying to my coordinate theta. Then you can just add that to my third component of my generalized external applied forces. So it's very simple. So it's not complicated at all. No thinking needed here either. So this is how it looks. So the moment applying in my system, I just add it to my third component. That's a scalar quantity, by the way. It's a scalar value. All right. And here comes this big mountain. Yes, sir. Oh, and I'm sorry. I was looking, why is that you looking at me so badly with the bad eyes? And I know why it is now. That's because I'm missing your coffee coupon. Sorry. I'm sorry about that. Next Monday, okay? Of course it matters. It matters. You need to take the sign into account. So the online participants, the question was, again, outstanding question, my friend, my only friend, by the way. So he was asking, like, what about the direction of the moment? Is it something that is immaterial, or is it making a difference? It makes a difference. You need to take this direction of the moment into account. Okay? All right. And I will bring you that coffee that you keep being my friend. I cannot lose my only friend. All right, so here comes the big mess. So we're going to redo the whole story, what we did for external applied forces, but for inertial forces. And it will look bad. It will be mathematically big mess, very involving. But forget about the mathematics, because you can use symbolic math tools, so it's not a big deal. What matters, what you're going to get end of the day as a result. So don't get confused about the detail, but think about the big picture. Where is that we are at? We here. Remember, we started here. So Newton's second law says external applied force is equal than inertial forces. And then came Dylan Brad with his big brains, and he figured out that this equation can be expressed this way. And he became to be super famous. But there was a bigger story than that. He recognized that the inertial forces can be treated same way than external applied forces. They're just forces, nothing else. Just forces. Bit more involving, but just forces. Okay, so what is it we need to do for this guy then? This is expressed in global coordinates. How you know that? Because the vector r, again, vector r consists of two components. And if I differentiate those two components with respect to time twice is not going to increase the number of components. They're going to just look different, but I'm not going to get like 5 components after that. That's not going to happen to you. So I need to use this mapping again. And now it becomes to be complicated. Because the mapping, you know that already is pretty bad. And this time I have my acceleration. Remember, the acceleration consists of 3 components. So this is a little bit of heads up warning for you. So it will look bad. But the concept is same. We're going to look inertia forces, which sophisticatedly saying is mass, and we don't want to say mass because we want to take all the particles into account. So we want to scan density of each of the particles within the boundaries of the body. Mathematically, that's equal than volume integral over the density of each one of these particles within the boundaries of the body. That's my mass. But I don't want to use that because I want to show off. I want to show off that, hey, look at me, I'm pretty good in the mathematics, pretty clever in the mathematics. And you can get this material that you can show in home. And not just in a home, but this week, Friday, if you go to visit in a bar, you can take your lecture notes with you and make some serious impression to your fellow students. What about that? Is that a plan? That sounds like a plan. Good one. All right. So here's my force. And then I'm going to use the concept of virtual work. Again, same story. I will have this virtual displacement. Very small displacement. Not because I like this very small displacement, but because it creates me this mapping. Opportunity to express this force component in terms of generalized coordinates. Okay? And this is how it looks when I do all this substitution. So far as everything is okay. I'm going to use this mapping. It's okay, still okay. Not too complicated, but I still have this guy here, which is expressed by using completely global coordinates. So I need to do something for that guy too. And what I can do for that guy is, okay, first of all, this one here, this partial operation, mass multiplied by acceleration, and this mapping is called generalized inertial forces. How many components? 3. 3 components. Okay, now I'm going to use a little bit of mathematical manipulation for my acceleration. So I expressed earlier my acceleration as it is shown here. So it was a translational acceleration. This was a tangential acceleration due to the rotation of the body, and normal acceleration due to the rotation of the body. So I will reorganize my acceleration expression in a way that I'm going to take my generalized coordinates, this one and this one. Oh, I see that this is a mistake. This shouldn't be power 2. This should be just without the power 2. And I express it using the matrix and acceleration of my generalized coordinate. And then just a component here, which is generalized coordinates 2. And then comes this in-volume substitution. Here it goes. So this is my acceleration. This is my mapping, which is already expressed in the details. And I will do it. I will substitute that to my virtual work done by inertia forces. This one goes here. This one goes here. And once I do this operation, this is how it looks. One more step ahead. It looked like this. There's going to be 2 components. One that is linearly related to acceleration. What is linearly related to acceleration is a mass matrix. And then something that is called quadratic velocity vector. Quadratically related to velocities. That's where the name quadratic velocity vector. So let me take a look at your faces. So, okay, so is it like this, still like this? No, be honest, please, please. Or is it more like this? Or is it completely like, no way? It's confused. Which is okay, because we don't care about the details. You just saw it how it happens, but you don't need to repeat it this ever. Well, let me take that back. The chances that you need to repeat this in your life is thin. So that's where we are. Now we're going to take a look at this component, this mass matrix. Mass matrix, and then I know that it's already time to close. I'm planning to close earlier today, and I'm not going to plan to have any breaks today because it's pretty soft material we are dealing today. So we don't need any breaks. What do you say? No breaks, for sure not. If it is interesting like it is today, you don't need any breaks. Okay, this is how it looks, my mass matrix. So this is full of mathematical operations, but let me make an interpretation for you. So I'm going to first thing that I would like you to pay attention is a dimension. So mass matrix will have how many rows and columns? 3, because of the generalized coordinates. This matrix is associated to Rx, Ry, and angle theta. So first corner, which is this upper left corner, is fully related to translation of the body. So if there's a translation of the body, what inertia properties is important in that case? Just the mass. Nothing else matters than the mass. Okay? So it's going to be 2 by 2 identity matrix located in upper left corner of this mass matrix. And then scalar component incorrectly written here. This is supposed to be scalar component, which is located in lower right corner of the mass matrix, is my mass moment of inertia. Mass moment of inertia is that how much inertia resisting the rotation. You take a pen and you rotate it in a one end, it resists that quite a bit, comparing when you rotate your pen in the middle. That because of the mass moment of inertia depends where you're rotating your pen. Okay? Makes sense? Okay, so just checking what are the comments from online participants. Is pretty small font, but I can see that people are not so happy because they feel that it's a little bit involving material today. That's okay, because this is the hardest you can meet ever in your life. Okay, let me take that back. In your master level studies in LUT, it's not going to get any more difficult than this. Trust me. So if you survive this, it's all downhill after this. Okay. Okay. So that's mass moment of inertia. And then the off diagonal component depends where your mass, center of the mass and the body reference coordinate system are located. So if they are same point, this off diagonal component will be equal to 0. Okay, one more story, and then I will go. I will stop today. So, okay, so here's my box-like body. And in my box-like body, I'm going to compute my mass matrix using 2 different scenarios. In one scenario, body reference coordinate system is located in the center of the mass, meaning center of the box-like body. And in another scenario, my body reference coordinate system is located in one corner of the box-like body. How much that will change the mass? If you're going to lift me here from my belt, or you're going to lift me from my neck, how much is my weight difference? How much? 10 kilos. Like no difference. But in my belt or in my neck, how much is my weight difference? zero. So it's all the time same. Here too. So if I'm measuring my mass using the coordinate system that is in the center of the mass or one corner of the box-like body, mass, weight of the body is same. It is same, because why it would change? This will be magic for weight losers, those ones that I want to get rid of some extra weight. That you're measuring it a different way, you will get the different solution, but you will not. You will not. Okay, do we have disagreement? Okay, now, my first component is just that I, integrate the density, which I'm assuming to be constant, over the volume of the box-like body. And the W, which is the thickness, this direction, is given. So then I'm integrating using my integration limits from minus L divided by 2 to L divided by 2, from H divided by 2 to H divided by 2. Very mechanical. So once I do my first integration, I will get L here. When I do the second integration, I will get H. So it's HLW. That's volume. Volume multiplied by density is mass. Okay? So this is identity matrix, 2 by 2 identity matrix. So my first component in my mass matrix is going to be diagonal matrix, where the mass of the body is located in the diagonal components. Okay, my second component will be equal to 0, because my body reference coordinate system is located in the center of the mass. And I'm not going to prove that in a further, but if you wanted to integrate this, you will make the same conclusion. So it will be equal to 0. And my scalar component will be my mass moment of inertia. So this is an equation multiplied by density that I'm integrating over the boundaries of the body. And now the boundaries are such that the W, the thickness, is given. And again, minus L divided by 2 to L divided by 2, minus L divided by 2 to H divided by 2. You do that, and you will get this one here. Mass divided by 12 multiplied by length power 2 multiplied by H of the body power 2. Something you can see from pre-calculated tables, so that there's no need to compute this material by yourself. Use CAD software, use pre-calculated tables. There's plenty of them to figure out what is a mass moment of inertia for a body. Okay, let's continue then. This is how it looks. So it's a diagonal representation, because body coordinate system is located in the center of the mass. Okay? Now, let me redo it. Okay, how much is a mass in this case? Because now the body reference coordinate system is located in one corner of the box-like body. Same. No difference. Integration limits will be different, because it's going to be 0 to H, L, 0 to W. Oh my God, this is supposed to be H. This is supposed to be H. No difference. So it's 2 by 2 matrix where the mass is located in a diagonal components. This cumbersome component, you just take these vectors, you integrate them using these boundaries, which is 0 to L. Now, because the way it is, this will be non-zero. For sure, this will be non-zero. So you do this first integration operation with L, you get this one. And then with H, sorry that I go this fast. And then you do all the multiplication, you will get the vector of 2 components. Okay, please understand this. Inertia properties will not change. Mass will be all the time same. Mass moment of inertia depends where you measure it. But once you measure it, it will not change after that. This component, which do not have a clear physical name, its representation will change, but it's compensated in my quadratic velocity vector. Okay. So my final component, mass moment of inertia. So again, I redo the whole thing. I have my equation here, which is a u bar x power 2, u bar y power 2. And when I do this all the math, I will get mass divided by 3 multiplied by length power 2 h power 2. Okay, you understood everything so far? Are you even a little bit with me? Okay, let me ask you this. Here comes the final solution. This is how the mass matrix look like. But my question is this. How much the body mass increase, decrease from case A to case B? All right, and and this is just a second. Okay, first thing is this. Okay, you don't see this yet, but I'm gonna show you this momentarily. Okay, 87 answers. Okay, so you see this. Okay, this is the first in-class quiz, the one that is still active. What is the correct solution? Oh, now you should be able to see. Let me take myself all the way up here. You still see this? This one. Okay, how many components? 3 components. So that means that this is off. This is off. The difference between A and B is this third component. And you can tell that, but when you look at how much is a vector u bar from the origin of the body reference coordinate system, where the position where the force is applying. Here the vector u bar, 0, meaning this is correct answer. Okay. Sorry. There are too many Akis, so it's I understand that you cannot handle that. Okay, this one here. Success rate is, oh, it's okay, but I was expecting more than that because as soon as there are 2 components, you're off. Because everybody needs 3 generalized coordinates. Okay? Then the next. How much the body mass will increase, decrease from case A to case B. And the cases are okay, so there is somebody sending these the bot is sending some messages in a chat. Okay, I don't know how to get rid of that. I don't know. Yeah, chat is not broken, but because this is the streaming is public. There are always these bots that recognize that there is a stream going on, and they will send these messages. Not much I can do. Just don't click. Whatever they say, never ever click. Because you're going to get a lot of viruses if you do so. But how much mass is increasing, decreasing? Remember, we speak about this L divided by 12. We discussed about L divided by 3. We discussed about many different things. Which side of these 4 options is correct? And yeah, don't click these links because the material you see in this class is better than these links. Way better. Those ones that are not seeing the chat, you can take a look at that later, but there's a bot, some kind of automated system that is sending quite a bit of crap. Okay, so let me take a look. Again, this one. Okay, so here it is. So 80, 70, 80 students at the moment. Last time I think it was 87 or something like that. But I'm pretty sure some of them we already lost their hope because we are not scoring 100%. I guess that's my interpretation. Okay, so now there is people are guessing that there will be a dance. I don't think so because this is not so simple. Yeah. Okay. Okay, are you guys ready? So in five, four, three, two, one, and dancing. Ooh, ooh, oh, oh. I was almost my breath was not able to go well because I recognized that the cream bar goes all the way to this right end. Close case. Ooh. Okay, so the mass is not changing. Mass is never changing, depending where you put your body reference coordinate system. Remember this, never ever changing. What is changing? Mass moment of inertia and this diagonal term. Those will change, but not mass. Okay, like I say, I'm feeling, earlier in this afternoon, I started to feel like a little bit under the weather, and that's why I would like to go home. So no breaks, just you guys back here. Oh, let me see. Okay, so there is a. Yeah, there is somebody that is not wanted to meet the dance. I think that's the only explanation. No, I don't do it. You saw my hand all the time, my hands all the time. So it wasn't me, and it is not Mustafa either. So we made a deal that we are not going to do that because that will be playing dirt, and we don't play dirt. We play fair all the time. Okay, all right, guys. So next week, okay, let me show what's going to happen a week from now. Okay, so it's going to be. Oh, there's a one more in class quiz. I think that I will save this because it's going to be pretty trivial and I need to explain this one more time to you. We're sort of going to take a look at the quadratic velocity vector, and this is it then. Then we're going to create the equation of motion. And then we start solving equation of motion in forward of time. So this is it, moment of truth. And it's okay. I mean, I say that people are crying usually when they see the kinematic analysis. It's fairly emotional, but nowhere near as emotional than dynamic analysis. People are sometimes crying really loud because it feels so good. I don't know what's going to happen to you, but it's okay to cry too. But if you feel that it becomes to be too emotional, I recommend online participation. So you can be in your private office or, I don't know, apartment and do all the crying. Okay? All right, so do we still have it? I mean, can do attitude. We still have it. You sure about that? But remember what I say, that things are getting progressively more difficult. I think that I was right about that. Now, I mean, that you jump in now, today, and there will be absolutely nothing you understand. Nothing. Okay, so let me close the recording and let me close the streaming. Online participants, I will see you on Monday then. Okay, thanks.